Great. So yeah, thanks for coming back. So we now are in our second lecture, and as I told you before, oh no, before I start, uh, hmm, this is not working. Second, view slideshow. Now it's working. Okay, before I tell you what we're going to do in the second lecture, I added a rudimentary page to my website, if you can, that has the slides and the notes for the first and second lecture. You can just scan this QR code, it should take you there. So yeah, just go there if you want to look at the slides or the notes on your own. But yeah, so maybe I'll skip this as well and just tell you more or less what we're going to do in the second lecture, which is essentially look at two applications in quantum information theory of what we did in the morning. And hopefully this will tell you a little bit about what you can do with SDP. So I tried to pick two applications which I think have slightly different flavors and illustrate why STPs are nice from different perspectives. The first one I think is going to be about PPT states, and this is going to illustrate how often we can use STPs to say something about very complicated sets by considering STPs which are simpler. So sort of relaxations of very complicated sets. Because in quantum information theory, we often look at sets that are convex, but from a geometrical or analytical perspective are very hard to understand how they actually look like and how to optimize over them. So prime examples are separable states, LHC measurements, correlations, blah, blah, blah. They are all very complicated. And if you want to optimize over them, that's usually very hard to do, both if you want to say something analytically, but also numerically. And they admit sort of nice approximations by STPs. In particular, for the set of separable states, you could instead look at so-called positive partial transpose states, PPT states, which you can then characterize by STPs. And we're going to look at them today. So this is one nice way STPs pop up in quantum information theory. And in computer science in general, actually, this is a very popular sort of mindset or framework to try to approximate complicated convex sets by STPs, or complicated sets in general. And the second thing we're going to do is to look at something that at first doesn't look like an STP, but if you do the right massaging with some matrix analysis, you will see it's an STP actually, and that's the diamond norm between two quantum channels. And what is nice is that both the primal and the dual, like the solution to these problems, also tell you something about sort of optimal strategies to distinguish quantum channels and so on. So you get some nice interpretation also from the results of the STP. Okay, so the geometric picture of this first example I'm going to consider, namely the set of PPT states, is as follows. So we are now going to look at a bipartite quantum system. So you have some Hilbert space X and Y, and we're looking at density matrices on these two systems. And you could, of course, look at the set of all states. And then there are the states which are not entangled, the so-called separable states. We're going to define them if you are not familiar with the definition in one slide. And as I mentioned, okay, here it doesn't look particularly complicated, but if you go beyond, let's say, one qubit and a qubit or something like this, it's actually a very complicated set. So instead of then looking at this set, we look at the so-called PPT set, which are then described by an SDP. And if you want to, let's say, optimize something over the separable states, this is very hard, but then you look at the set of PPT, which is strictly smaller than all states, and hopefully the optimizing over this set will not yield a very different answer compared to optimizing over this set. So this is somehow the philosophy, and optimizing over this set is actually something you can do with an STP and in practice. So just to make things a bit more precise, what are separable states? Well, these are just convex combinations, also called product states. So we say that a density matrix is separable if you can find these probabilities PIs and density matrices rho IA and rho IB, such that this matrix rho AB is of this form. And we say that a state is entangled if it does not admit such a decomposition. Okay, and determining whether a state is separable or not is hard, because I mean, okay, if I give you such a decomposition, it's of course easy, but actually characterizing this set is a very nasty problem. And therefore, even though it's a convex set, clearly if I look at a linear convex combination of two separable states, then you again have a separable state. However, optimizing linear functionals over this thing is generally a pretty hard problem. Now, what is one thing we can do, and this is I don't know, a 30-year-old idea, maybe 40-year-old, I don't know, it's a pretty old idea, is just to look at the so-called partial transpose, okay? And what do you do? What is the partial transpose? You have some bipartite matrix, and I'm going to define it with respect to a basis, but the partial transpose is actually basis independent. One can show that. And what it does is, of course, you can expand any bipartite matrix X in terms of some matrices Xij on the first system, and then sort of the matrix elements on the second system. And this partial transpose on the second system is just a linear map, which is going to swap the I and J to J and I. So you just swap those coordinates. Why is it called a partial transpose? Well, if you only had one matrix over here, this would be exactly the transpose, right? You just swapped those entries of the matrix. So we call it a partial transpose because it's acting only on the second half of the system. And we call a state PPT, so positive partial transpose, if it's acting with the partial transpose on it, gives again a positive semidefinite matrix. All right. So PPT again stands for positive partial transpose. Now, one key observation is that if rho AB is a separable state, then it is also PPT. And proving this is very simple, because let's say I have a decomposition like this. Okay, then if I apply the partial transpose, it's only going to look at the transpose of this guy here. And if you have a positive matrix, applying a transpose to it will again give you a positive matrix. So we immediately get a positive, of the composition of this form for the matrix rho AB with the partial transpose. All we need to do is apply the transpose to this second bit over here. Okay, but so far so good. So we see that somehow if rho AB is separable, then rho AB is PPT. Any questions so far on this idea? Yes. Yeah. So I mean, essentially, what you can do is, you can always decompose any matrix. I mean, uh, t- t- sure. Let's do that. That's a good idea. So let's take our favorite friend, the maximally entangled state. So the maximally entangled state, I'm not going to normalize things, okay, so it's a bit easier. So on let's say 2 qubits, so it's just this state is the so-called maximally entangled state. So let's look at the density matrix you get from this pure state, and it's gonna be 0 0, or maybe I'll be a bit more pedantic with the tensor product so that it's easier to see what's going on. So it will be 0 0 tensor 0 0 plus 1 1 tensor 1 1. So these are the diagonal elements, plus 0 1 tensor 0 1 plus 1 0 tensor 1. So yeah, so this is the density matrix corresponding to the maximally entangled state, right? Now, if we do the partial transpose, what do we have to do? I'm making it act on the second system. So we do nothing to this bit of the matrix, and we do a transpose to the second bit. So this just transpose is just flipping these two guys, right? So this bit remains exactly the same. So it's going to be 0 0 tensor 0 0 plus 1 1 tensor 1 1. Do you agree? Because here nothing changes if we flip. Now let's go to the second part where there is some action. So it's going to be 0 1 tensor. Here we have to flip them 1 0 plus 1 0, and here again we have to flip them. Okay, and this sort of exercise we could do with any matrix, really, right? Because all you could you can expand any matrix as some sort of linear combination of brackets of this form, like ij tensor kl. So you just expand the matrix in this basis, and all you need to do is sort of flip the second part. Yeah. Yes. This expansion is unique because matrices of this form, they form a basis for the set of matrices, an orthonormal basis, even in fact in the Hilbert-Schmidt scalar product, and therefore the expansion is unique. Does that make sense? Okay. And I mean, all I'm doing, this is just like a fancy way of saying, like, this is row and column addresses, right? And also the tensor product. So essentially, I'm just specifying the entries of the matrix and writing it in terms of that. Yeah. Yes. If this, so the question is, what is sort of the adjoint of this map? Yes, it's self adjoint. Yeah. So if you once you do the Hilbert-Schmidt, Oh no, it's a linear map. It's a linear map. So if we had like I don't know some let's say if you had an alpha in front of here, like as it's a linear map, then we are not we're not doing some sort of yeah. It's really just flipping. Yes. Sure. That's a good idea. Thanks. And we'll make my job a bit easier next. Um, so the psi was just 1 0 0 1, right? So this is the diagonal. The first term 0 0 0 0, and then the second term is 0 1 0 1. So it's going to be like 1 0 0 0 0 0. Okay, and this is the first matrix, right? The our maximally entangled state. And now once we look at identity tensor T of this will be 1 0 0 1. Okay, and what do we observe now? And can someone tell me what is interesting about this matrix here? Like, is it positive? No, right? Because this part over here, this is like a Pauli X, right? So if you have a positive matrix, every submatrix also has to be positive, right? And clearly this matrix here has an eigenvalue -1, like the minus. If you just look at it as a 2 by 2, like the minus state, right? So we see that if we apply the partial transpose to the maximally entangled state, it is not positive anymore. So, but we showed that if rho AB is separable, then rho AB is also PPT. We saw now that this guy is not PPT, therefore it is maximally entangled. Therefore it is entangled, as the maximally entangled state should be. Questions? Yes. No. It's you're right. So what? But what? So if rho AB is PPT, then we don't know much, right? But the other direction, if rho AB is not PPT, it must be entangled. So it's not an equivalence, right? Other questions on this? Yes. Fantastic observation. So in the first class, I mentioned that there are these completely positive maps, which are maps that sort of, if you tensor them with the identity on any system, they will still map positive matrices to positive matrices. And I said it's maybe not the most trivial thing to construct a map that is positive, but not completely positive. And the standard example is the partial transpose. Because if you just let it act on one matrix, like taking the transpose of a matrix, will map positive matrices to positive matrices. But we saw that for if you tensor it with the identity, it will no longer be necessarily the case. So yeah, thanks for, I almost forgot to say that. Thank you very much. Yeah. Other questions, observations? Nope. Okay. Yeah. Thanks for helping me out when I forget to say important things. Let's continue. Right. So, what is nice about all of these things we were discussing, and you already were able to detect a few points, is that essentially requiring that a state is positive semi-definite is something that is natural for STPs, as we discussed, but also requiring that something has a positive partial transpose is another PSD constraint, right? So it's just applying the partial transpose on a state. So it essentially, and because of this, we will be able to use this partial transpose as a way of relaxing the idea of optimizing over separable states, right? So, and it will be able to detect many entangled states, as we've just seen in the example. If for instance, for the maximally entangled state, we can easily detect using the partial transpose that it is indeed entangled. And for very small systems, it is even an equivalence. So if you have 2x2 or 2x3 systems, partial positive transpose states are precisely those that are separable, going back to your question. So if you're in very small dimensions, this is actually exact. So what does it mean? Well, let's say that you want to optimize over separable states. We have no idea how to do that, but STPs come to our rescue, okay? Because what we can do, for instance, is let's say you want to optimize your favorite observable age, let's say the energy or whatever it is, your favorite observable over the set of separable states. Have no clue how to do this. This is a very hard optimization. But what we can do easily is to just, instead of optimizing over separable states, we'll now optimize over states that are PPT. Okay? And this is a PSD constraint. We're just applying a linear map to this matrix rho AB, which is the partial trace. Oops, sorry. And so this is a valid SDP, okay? And the objective value stays the same. So sorry, the objective value, no, the objective stays the same, but we just enlarged the feasible set. So all separable states are PPT. So all states that are separable, we're going to optimize over, but we're also going to optimize over certain entangled states that nevertheless remain positive once you apply this partial transpose. Okay, so in principle, as you're optimizing over a larger set, the value can be a bit larger than only over separable states, but at least it gives you something you can compute efficiently and already rules out some entangled states, right? You're actually looking at a strictly smaller set of states than just optimizing over everything. Okay, so and because of this, the optimal value of this thing will give you an upper bound on the optimal value if you optimized over all separable states. Is the philosophy or the idea clear? All right. So and then we can also write the dual of PPT, as we discussed. Finding this dual is a bit more advanced, or not advanced. It requires a bit more work than just the recipe I showed you in the morning. In the notes, it's explained how you get this. But what you then get is some sort of some linear matrix equality that you need to fulfill, and you need to optimize over parameters lambda. And what is the nice thing, right? If you get a feasible point, you know that for all PPT states, you have that trace age rho will be smaller equal than lambda. So if you have any feasible point, you know that for all PPT states, this thing must hold, right? So in particular, this has a very nice physical interpretation for this dual. Because let's say you're given some state, rho, and you actually measure the expectation value of rho on age, and you get a value that is strictly larger than lambda. What does this imply? What do you know from this? Exactly, that the state is entangled, right? So so if you just find any dual point that is feasible, you can use this information to potentially detect some entangled states. Just measure what is the expectation value of age. If it's above a certain threshold, then you're good. So this is how duality theory also helps you to get something like something, maybe practical is a strong word, but there's a physical value to it as well. Okay. So yeah, I just want to show you another sort of neat example of what you can do with this kind of stuff, and it's going to be solving a kind of oh, sorry. So imagine that you want to compute what is the maximal overlap of a separable state with the maximally entangled state. Okay, so I think I didn't write this down over here, but imagine that we are trying to compute what is the maximum overlap of separable states with this maximally entangled state over here. So in some sense, like the separable state that approximates it the best. This is a very hard optimization problem, but we can, of course, also look at what is the maximum overlap of PPT states with the maximally entangled state. And this is precisely the sort of problem we were looking at before. You just, instead of optimizing, you choose as age the density matrix corresponding to the maximally entangled state. Now, so we're going to show that it's at most 1 over the dimension. And this bound is tight because, yeah, it's not too difficult to find examples where this is indeed the case. If you want, just like, I don't know, the zero state does the trick, right? And how are we going to show this? Well, remember that I told you before that when you were doing Slaters, the conditions and so on, then often just trying with the maximally mixed state is good enough. Well, it turns out that if you do some matrix tricks, this is indeed the case also here. So if you look at what this maximally entangled state is, when you partially transpose it, it's precisely the unitary that corresponds to the swap. Okay, but I mean, maybe if you don't know what the swap is, that is perfectly fine. The only thing you need to notice is that this matrix over here has operator norm, has largest eigenvalue 1. Okay, so you see that this part, of course, has maximum eigenvalue 1, this one as well, and it's in direct sum, and this one has eigenvalues 1 and minus 1. So the maximal eigenvalue of this matrix, which is the maximally entangled state partial transposed, has maximal eigenvalue 1. So this implies this inequality over here. So the maximally entangled state partial transposed is smaller than the identity. Okay. Another thing you should observe is that if we partial transpose twice, we get the same state back, right? Because it's just you flip once and then you flip again. So we have that. So you have that identity tensor t squared just equal identity tensor identity. So if I look at trace of the maximally entangled state with any other matrix rho AB, I can write the same. This is the same as trace identity partial transpose twice, right? And going back to the question we had before, I can look at the adjoint. It's, again, the partial transpose. So this is going to be the same as trace identity partial transpose. Okay, so I can do the partial transpose twice. Okay, now if this guy is a PPT state, this thing here, so if rho AB is PPT, this thing over here is going to be positive. And by what we discussed before, this thing here is smaller than the identity. So it follows that trace sigma sigma rho AB is smaller equal identity trace identity over D rho AB, and this is 1 over D. What does this calculation show? That we can derive this nice upper bound on the overlap between any state that is PPT and the maximally entangled state by some very simple matrix manipulations, right? Whereas if we were actually optimizing over the set of all separable states or something like this, this might actually be a harder problem. Okay, so this is a not too deep example, but the nice thing is somehow that you can you by doing this relaxation, you can say things which, if you were optimizing over all separable states, might actually be hard. It's not really the case here, but in general, it's a bit harder. Okay, so this is all I wanted to say about that example. So before we move on to something significantly more involved, maybe it's now a good time to step back and ask if there are questions, comments. Nope. Okay, so maybe it was tactically not very smart to present the I think the most challenging part of the of these two lectures before we all go to Camarões, but bear with me. It is very nice. Okay, I at least really like what I'm gonna show you now. So hopefully you like it as well. Hopefully I'm able to convey how this bit. But we also have quite a bit of time to go through this. Okay, so please feel free to interrupt me as much as you want. It is gonna be a bit more involved than what we had before. So first, in the morning, I talked about this Krauss decomposition for these completely positive maps, And now I'm going to show you another way we can understand completely positive maps, which is the so-called Stein-Spring dilation. Okay, so this is actually equivalent to the cross form we had in the morning. Okay, and it looks like this. Some people also call this the church of the larger Hilbert space. So it is essentially saying that everything is you can replace isometry here by unitary without losing much. So let's just do it with unitaries. Might be a bit closer to what you're used to. So it says that if you have a CPTP map, so just remember that this means that so CPTP map phi. It means that if you take phi and you tensor it with the identity, this will be positive for all rho positive. And in the morning, I give you this example of this map phi of rho just being like unitary conjugation. Maybe this is something you're familiar with, just unitary evolution. And what one way of understanding Stein-Spring dilation is saying that this is all there is. So if you want to get all completely positive maps, as long as you're willing to work on an enlarged system, all there is are unitaries. So essentially, the Stein-Spring dilation says that for all CPTP maps, or for each CPTP map, there exists a unitary U and an auxiliary and an auxiliary space Z, such that phi applied to rho is the same as trace over Z of U rho tensor 0, 0 on Z. Okay, and if you there, I've written it with an isometry, and then sort of the isometry is just sort of tensoring with 0. So it's like yeah. Anyways, let's maybe forget about it. So what is this saying? This is saying that if I have a CPTP map, I can always understand this as unitary evolution, but on a larger system, such that system and this auxiliary system start uncorrelated. I do the unitary evolution, and then I discard the other system. Okay, so in some sense, unitary evolution is all there is. Questions about this Stein-Spring dilation? Yes. Doesn't so okay. So this is a good question. In principle, I could do any state over here, any pure state. So because if I consider like U and then I compose U with let's say any unitary of the form identity tensor, I don't know, what is another unitary? Let's say U1 and then no, let's I don't know, R, some unitary R on the second system. When I take the partial trace, this won't make a difference, right? So we can just set it to 0, 0 without loss of generality. But it's important that they're not. The important fact is that they're uncorrelated at the beginning. So somehow they're uncorrelated, I make them interact, and then I trace out. Other questions? Yes. It can always be made pure. Okay, so and again, there is this sort of church of the larger Hilbert space idea that if you want, you could also, if you have such a decomposition with a mixed state, then you can purify that state and bring it into this form again. So If you don't mind enlarging the auxiliary space a little bit further, then you can make it pure as well. Other questions? Nope. Then let's continue. So this is the composition for completely positive maps. So we had the Krauss in the morning, and we have now this Steinspring. They are equivalent. And yeah, now if you have a general linear map, you also have something like a Steinspring dilation. And it tells you that if you have any linear map, it can be written as acting with some matrix A0 that goes from the space X to a larger space Y. So the map phi, maybe I should write it down now. So the map phi, it is gonna go from the matrices on X to the matrices on Y, okay? And what I'm saying is that you can write any map like this as sort of multiplying with a rectangular matrix, that is a matrix that goes to X to Y tensor Z on the left and on the right, and then you trace out Z. Okay, so any linear map can be written like this. You'll have to believe me about that, but in the lecture notes, I do have a proof. It's not very, very complicated, but probably you won't learn that much from it. And what we see here is sort of a generalization of what we had before, but now with the difference that for completely positive maps, you have that A0 and A1 are exactly the same state. Sorry, the same matrix, okay? And you might be wondering why I'm telling you all this. And the reason is that this is going to be the starting point of the SDP for the so-called diamond norm. All right, but maybe before that, I should tell you what the diamond norm is. Okay, so what is the diamond norm? The diamond norm asks the following question. Okay, it's again some sort of discrimination problem, but now it is between two quantum channels and not two quantum states, like we had in the first lecture. So the idea is as follows. Imagine I give you access to a black box, and I promise you that this black box is either described by this channel phi 0 or the channel phi 1. So a quantum channel is just something that you feed it some input, it will give you some output, okay? And you feed it some input state, it give you an output quantum state. And your task is now to decide whether I actually have given you the channel phi 0 or the channel phi 1. But we're going to do this in a slightly modified way. Namely, you're not only allowed to put an arbitrary state into phi 0 or phi 1, like in this black box, and then doing a measurement. You can also let the input state be entangled with some other register Z, okay? And then the channel will only act on X, so nothing happens to Z. And then you're allowed to measure both the output of the channel and your other system Z. So mathematically, you're letting the channel phi B tensor identity act on the state rho X Z. And the question is, if I allow for auxiliary systems of arbitrary size, what is my optimal probability of guessing channel A or B, 0 or 1 correctly? Okay, so this is the task. I have to distinguish two black boxes. Each of them appears with probability 50-50. I can use arbitrary inputs, arbitrary outputs, include arbitrary measurements, including those that are initially entangled. And I'm asking what is the optimal strategy for this problem. So is the operational setup clear? Okay. And so from a quantum information theory perspective, this is a very natural problem. And it turns out that the optimal probability of success is given by something called the diamond norm between channels phi 0 and phi 1. Okay. And at first, it might not be, and note that there are certain things that are interesting here. For instance, I'm allowing for arbitrary dimensions in this auxiliary system Z. So as big of a state, I mean, doesn't there are no bounds. You can have it as big as you want. And what we're gonna see in these last, let's say, 30 minutes or so, is that actually you can compute this quantity as an STP. And this is a nice result by Watrous maybe 20 years ago or something. Yeah. So the exact reference should be at the end and also the lecture notes. And why am I presenting this to you? Because it's not obvious at first that this is an STP. So I'm just going to show you that sometimes you have to trick a little bit to massage quantities into an STP. And this is a bit of an art form, although there's some standard tricks there as well. And we're going to see one of them soon. So first, I should let you know that actually allowing for this extra system over here can increase your probability of success. So there are examples of quantum channels where if you're not allowed some sort of extra entangled state for which you can send the channel, the probability is actually worse than if you have some entanglement as a resource. And from a mathematical perspective, this comes from the fact that if you look at the so-called one-to-one norm of a map, this is not stable under tensoring with the identity. So what is the one-to-one norm of some map here? Okay, and you should always think of this as some sort of difference of channels. So this will be the maximum trace norm of phi of x, given that x is a trace norm smaller than 1. So as I'm telling you this, I'm realizing probably I should tell you what all of these norms are. So essentially, the trace norm, so this x1 for a matrix, is just the following thing. So you take a matrix, multiply it with its adjoint, and then take the square root. But if x is greater or equal than 0, so for positive matrices, the trace norm is then just trace x. So, and for general Hermitian matrices, so if x is Hermitian, then the trace norm is just the sum of the absolute values, eigenvalues, and absolute value of the matrix X. Okay, and this is a norm on matrices. So essentially, the way you should think of this is, given some map, and I know that I'm feeding it something that has norm at most 1, how much can this map expand or shrink this norm, right? So it's asking what happens to matrices once I feed them through this map with respect to this norm. Is it getting bigger, smaller? What is the maximum that this norm can change somehow if I feed it x? And And if you think in terms of differences of channels, this gives you a way of telling you how distinguishable two channels are. And the fact that if I look at this norm and I tensor it with the identity, the fact that sometimes this can be much, not much, but sometimes this can be larger than this norm means somehow that once we allow for entanglement, then we can also increase the distinguishability between different maps. Okay, so this tells us that somehow looking at the channel itself, if you allow for entanglement, is not enough to quantify its power. We also need to take tensor products with the identity. And this gives rise to the so-called completely bounded norm. So it's or diamond norm, which is essentially this one-to-one norm, but now we also allow for tensoring with arbitrary identities. Okay, so we look at the initial map and then tensor it with any identity. And this is often sort of the right thing to look at in quantum information theory when you're, oh, sorry, I forgot this. Actually, I can't give I don't know a simple example. Does anyone in the audience know a simple example? No, I have a quantum channel. Oh, okay, yeah, transpose. Okay, fair enough. Thanks. No, just an example, a simple example of this inequality, and it's already on the map on the board. Thank you, Richard. So, um, right. So let's do that one. So the in fact, so if we take the just to show if you have phi just being the transpose, then in that case, this will not change the spectrum, right? So if you just act with the transpose on a matrix, this will not change the spectrum. So we have that. So if we do the one norm of the transpose of X, this will be X again, so it will preserve that norm. But we can just look at this example over here. Okay, so here, the initial one norm of the state, this is a pure state, so it only has one eigenvalue, which is 1. Okay, so now let's look at what happens. So we know that the one norm of this guy, because it only has one eigenvalue, which is 1, is 1. But let's look at what are the eigenvalues of this thing. Well, certainly there's an eigenvalue 1, another eigenvalue 1, and the eigenvalues of this thing are 1 and minus 1. So we see that the sum of all the eigenvalues in absolute value is 4, right? So this already gives you a nice example. So because we see that because of this equality here, when we are only acting on one system, the one-to-one norm of this guy will be at most 1, or is 1 actually. And here we've seen already one example where it has increased by more than 1. In fact, it has increased by a factor of 4, right? So this gives you. By the way, I think I screwed up this example because of normalization. It should be 2 and 4. Sorry. Yeah. Okay. Uh, is this a bit clearer now? And thanks for giving me a very easy example already on the board. Other questions? Nope. All right. Yes, please ask as many as well. Yes. So this is this observation here. So so why do I like this? Why is this definition nice? This definition is nice because it shows you that like one nice property the diamond norm has is that if you tensor the um, let me do it over here. So let's say if you do anything like this, so if you tensor two quantum channels and you look at the diamond norm, then you can easily sort of upper bound it in terms of and doesn't matter what the dimensions of these two guys are, because you can easily do the following thing. You can write a channel phi1 tensor phi2 as identity on the first system tensor phi2 composed with the this thing, and from this it easily follows, no matter what dimensions you have here, one can show that from this it follows that this is smaller equal than the diamond norm of the first one times the diamond norm of the second one. So you have the submultiplicativity property, but in principle you're right in saying that this thing here is completely unnecessary. In principle, it suffices to take the tensor product with the identity on something that has the same dimension as x. Okay. Other questions? All right. So hopefully I could motivate this a bit operationally, that this is sort of a right distance between channels in the operational setting when you also allow for entanglement. And why are we talking about this? Because this has a nice STP formulation that is non-obvious at first. So given that it has this nice operation interpretation, you might actually want to compute this. You know how well you can distinguish two channels no matter what you do. And what did Watrous show? Okay, Watrous showed the following thing: that if you have two completely positive maps, psi 0 and psi 1, and you have these Stein-Spring dilation decompositions for them, and oh, the pointer is not working anymore. Oh, no, it is. You have these Stein-Spring dilations. Remember, they always exist for any completely positive map. Then he showed that the diamond norm is the same as the maximum fidelity between the outputs of psi 0 on row 0 and psi 1 on certain row 1, where we are allowed to optimize over these states. Okay, so it takes some effort to get this decomposition. And just for you remember what the fidelity is, it is just this. I think it is dying, so I'll just point to things, or maybe I can use my mouse. Should use the mouse, should be fine. So this is the definition of the fidelity between two quantum states. And another nice equivalent formulation for the fidelity is the following one. So it's the maximum of trace y plus y star such that this inequality holds. Okay, so this is another thing that you have to show. It takes a bit of time and effort. We're going to do it. But why is this already something very nice, this formula for the fidelity? Because when you look at this quantity over here, it already, at first it looks like something very nonlinear and complicated. You have the square root of two matrices, and then you have this one norm. So you might be like, oh, this looks very nonlinear, looks kind of nasty to control. Thank you. And but now it turns out that you can write it in this form over here, which is an STP. And we know that once we have STPs, we have lots of things we can play with, like duality and finding feasible points and so on. So even though computing this thing, getting like a closed formula for whatever this is for two matrices P and Q is probably very hard, you at least have something you can play with to get feasible points, bounds, and so on. But it also gives you an alternative way of computing this thing, because you don't have to compute this square root, you don't have to this one, you can also just solve this STP. And maybe so that I completely lose you now, I'll also try to quickly explain this. Sorry, probably this is not very too late in the afternoon to go through this, but I just want to mention the Schur complement once during this lecture series, so that's why I will not skip it, because I think it's a nice trick that people should know. Okay, so don't worry about the rest of the proof. Just note this Schur complement trick. Okay. So how are we going to show this formula here for this quantity in terms of an STP? The trick is as follows. Okay, one can show that if you have a matrix like this, it is positive semidefinite if and only if the matrix P minus the inverse of Q conjugated with Y is positive semidefinite. Okay, so why is this something very, very useful? This is something very, very useful because it lets you take things which look significantly more complicated and nonlinear, like equations like this one, and transform it into some sort of positive matrix constraint. Okay, the rest of the proof, I think I'm gonna skip. But essentially, remember this Schur complement trick, which allows you to say things about quantities of this form by enforcing positivity constraints. So, and then you can do some matrix analysis, some polar decompositions, and so on to actually arrive at the end at something that looks exactly like the fidelity. But the Schur complement trick is the important thing. Okay. Now, why is this sort of a nice thing? Well, let's just piece together the things we learned in the last few slides. We know that, as Watrous showed, that you can compute the diamond norm by looking at these maximum fidelities. Now, we showed that the fidelity can be expressed in terms of of an SDP. So in some sense, we have to optimize this thing over here once we apply maps to P and Q, right? So this will combine well with other linear maps as well. And this is how you get watch this nice result that the diamond norm between, let's say, two quantum channels admits this nice SDP form, because it's just going to be the maximum. Remember, like now that we are maximizing over the input states here, the first one, then the second one, this is just the Watrous result. So for a fixed rho 0 and rho 1, this would just be the fidelity between psi 0 rho 0 and psi 1 rho 1, right? But by the Watrous formula, we also need to optimize over all possible rho 0 and rho 1, because then this would give us the diamond norm. And this is sort of the magic of combining this SDP formulation of this fidelity with these maps, because the fact that everything is linear, everything respects this PSD, means that we can combine the two things and optimize the fidelity while also optimizing over arbitrary rho 0 and rho 1. Okay? And this is sort of, at least at first, a not very expected result, that you can take something like the CB norm between two channels phi 0 and phi 1 and express it as this nice SDP. So yeah, any questions on this result? Okay, so yes, here, or sorry, could you speak a bit louder? Mm-hmm. So we have the fidelity between P and Q. Okay, so maybe I'll just do the step-by-step on the board. So sort of the result is that if I take, let's say I want to compute, like, how did I call it, the f of P and Q, right? I can write this as 1/2, like maximum 1/2 trace y plus y then of all the matrices such that P, Q, Y. Okay. Now, and the other result is that if I'm having, let's say, two channels, phi 0 and phi 1, and I want to compute the maximum, sorry, the CB norm, this is the same as maximum over rho 0 and rho 1 of the fidelity, right, between phi 0 . So the magic is that if we forgot about this thing, we can write this thing as an SDP, right? So let's just forget about the maximum here and just insert what we have here. So we just take whatever was here before, so it will be 1/2 trace y plus y star. And then we just have to put this thing over here. Okay, so Max. This is if we were forgetting about this maximization first. But now this, yeah, sorry, my handwriting is terrible. Let me start over there. So where was I? Yeah. So we have the F. Okay. Now this is the, if you weren't this is if we were not optimizing over row 0 and row 1, which is not so. The nice part of all of this is that if we, in addition, also optimize over row 0 and row 1, right? So now we have here row 0, row 1. All we need to do is add the points that row 0 is positive, row 1 is positive, trace of row 0 is 1, trace of row 1 is 1. And why is this very nice? Because before we added row 0 and row 1, this was an SDP, but the other points, the other optimization points we added are still STPs. We just added additional variables, row 0 and row 1, but all the further constraints we added still have the general structure, right? Everything continues to be linear and so on. So we are just enlarged the space we are optimizing over, but we didn't change the fundamental structure from SDP into something else by optimizing over all possible states, row 0 and row 1. And this is why it's super nice that we can actually express this fidelity in terms of this SDP, because then we can then do additional optimizations on top without changing the sort of class of problems we are optimizing over. Okay, and in this case, this gives you an SDP for the diamond norm. Is the idea a bit clearer now? Yeah, exactly. Yeah. And you could even generalize this to beyond CP maps. Okay, I think so I'm gonna essentially skip what I planned for the last minutes. I'm just gonna mention what I wanted to talk about, which is just to say that sort of these things are not too far away from things people are studying right now. So just to connect you a bit closer to current research, okay? So as I mentioned, this SDP form of the diamond distance, I think, is 20 years old, but people are looking at very similar quantities and asking whether they admit efficient representations like STPs or not, and how and related questions. So, for instance, you could, instead of looking at this one-to-one norm, you could look at what happens with P to Q norms. Essentially, the P norm of the output state divided by the Q norm of the input. And the nice point or the bad point, depending on your point of view, is that these things can encode very hard combinatorial problems. And then, so for instance, there was these very recent results from last year that show that for instance, if you restrict, for instance, computing this one-to-one norm to traceless matrices, then this can, for instance, be NP complete. Or even if you restrict your entanglement breaking channels. And that approximating these norms is in general a very hard problem. So what I wanted to say is that it is not always the case that you can find such nice, efficient decompositions. When they appear, they should be celebrated, and that people are still trying to find ways of sort of get these approximations by, for instance, looking at CB, sort of these completely positive relaxations and so on. So this is still the topic of recent research. I think I put the reference. Nope, sorry, but it's a paper by Omar Fauzi that came out last year. In the lecture notes, I'm sure I put the reference. And all I wanted to say is that sort of these questions of what problems in quantum information theory admit nice STP representations or not are still very much the topic of active research. But sort of the takeaways for today should be that if you're optimizing over separable states, the first thing you should do is to look at PPT states. They admit nice STP representations, and you can use the tools we developed in the first lecture. Other times, if you work a little bit, you can transform something that doesn't look like an STP into an STP. And I didn't have time to go through this properly, but often the key trick is this thing called the Schur complement. Look it up; it's nice. Maybe I'll change my plans a little bit for tomorrow to explain this properly. Think about it, and also that sort of computing these norms and things like that is still something people are that is still the topic of active research, and this is a very special case, and it's not always that you can find such nice SDP representations of things in quantum. And with that, yeah, do we have more questions? Yes. Uh-huh. Yeah. So there are like these. I think they're literally called min max theorems, which tell you that when you have such problems, you can exchange the logic. What do you mean by always? So like for these sorts of problems, usually it's not. Yeah. But I think if one would have to be a bit more careful and precise when. I mean, there are counterexamples where exchanging the order will change things. Yeah. If you're not careful. Other questions? Yes. So okay, so I guess so. Let's say if you have three systems now, right? Well, I guess first of all, then even the definition of entangled is a bit more delicate, right? For bipartite, I think it's very clean. So you could ask, for instance, that it's like let's say if you have like something like completely separable, right? So just to because if you have, let's say, even for three systems, let's say K systems, you can uh, demand say that a state is separable if you have some, let's say, decomposition like this, which I think people would usually call it completely separable. But as far as I know, there is no SDP formulation of completely separable states. So I don't think that in general you can easily say this, but I'm a bit out of my depth here. But I don't think there in general you can. Mm? Mm-hmm. Yeah. Yes. Yes. Yeah. Thank you, Rashid. So indeed. So maybe connecting to the lecture before. Also, if you are looking at things like error correction, I think. Well, I was talking about Omar before with these norms. Omar Fauzi also has some recent work on these threshold theorems. So which essentially tell you, right, that if the noise is below a certain threshold, then you can do error correction, and you will actually reduce the noise by doing it. Um, and well, if you have just some general noise map, let's say if you have a depolarizing channel, for instance, then you have a very clear noise parameter P. But if you're just comparing two unitaries and you want to say how well one unitary approximates the other, then there is no sort of clear parameter like the depolarizing probability that tells you how you should measure this noise. Um, and it turns out that the right notion there is also the diamond distance between the two channels. So if you look at sort of the idealized implementation of your gate and the noisy one, the correct way to define to quantify how noisy this is by looking at the diamond distance. And the reason why this is a very good notion, or the correct notion, is precisely what I explained before and erased, uh, because these stabilized norms, they talk well with like not doing like different subsystems doing different things. So before we wrote like an inequality like this one. And why does it matter? So, and to talk about things like fault tolerance, because it's telling us that if we know somehow what is going on with phi one, so imagine this is like one part of the system. This is another part of the system, right? So this is telling us that if we know something about what's going on in this part of the system and another part of the system, then we can control what is happening when we look at the two systems at the same time, right? We can bound the joint behavior by the individual behavior. And this is why notions like these completely bounded norms are important when you're analyzing complicated systems which correspond to lots of different parts, and you only know how to control them individually. Because the diamond norm allows you to say, like, hey, no matter what's going on with the rest of the system, as long as I know that the diamond norms between these two guys locally is close, then also no matter what the rest of the system is, the outputs will be close. So these completely bounded norms, they are very useful when you want to extrapolate from something that is only going on in one bit to when this is only part of a larger system. Another reason why you might want to get upper bounds or lower bounds between DCB norms if you're doing, let's say, fault tolerance experiments. And then again, STPs are nice, right? Because you can not only compute these things, but maybe you can get some witness that tells you that the diamond norm is already below threshold or something like this. So yeah, this is another nice application. Yeah, thanks. Other questions? No. So before we finish, just tomorrow, I'm gonna give you a quick overview of how people actually, some approaches to actually solve these STPs. Like because so far I just kept saying that you can solve them efficiently, but tomorrow we'll try to explain at least one or two approaches to actually solve them on computers. We'll just touch the surface. It's going to be some sort of overview, and at least hopefully you're going to understand why in practice solving large scale STPs is still kind of hard. It's polynomial time in the dimension, but a kind of bad polynomial. So yeah, anything else? Then I guess I see you at Camarões in 3 hours, right? Yeah, okay, thanks.